Welcome to paper 31. This is a stats paper from the Edexcel A-Level 2025 series. All right, question number 1. A1, it tells us the probability of them both being yellow is 3/16. So if I do a third times the probability of it being yellow in bag B, I get 3/16. Multiply both sides by 3. The probability of being yellow in bag B is 9/16. That gives me all the information I need to fill in the tree diagram. So we've got 5/12, 4/12, 3/12, and then 7/16, 9/16, and so on for bag B. For part B, finding the exact probability that at least one of the two beads selected is yellow, I'm going to find the probability that none of them are yellow and subtract that from 1. So the probability of it not being yellow in bag A is 8/12. The probability of it not being yellow in bag B is 7/16. So I'll multiply those together and subtract them from 1 to get 17/24. For part C, the probability of W given X, well, the probability of W intersect X is going to be a green picked on the first one, because that's the only point where a green can be picked, followed by the yellow on the second one. So it's going to be 3/12 multiplied by 9/16, divided by the probability of X. Well, we've already calculated that. That's 17/24. So it gives us our calculation 3/12 times 9/16 over 17/24, and that equals 27/136. Question number 2, this is the runners in the athletics club. Well, to find the mean, we'll divide the sum over the number. So the sum's 6612 divided by the 120 runners comes out as 55.1 seconds. For the standard deviation, we can just use the formula. It's the sum of x squared over n, subtract the mean squared, and then all of that square rooted. So 364,902 over 120, subtract 55.1 squared, and square root all that. Actually simplifies quite nicely. We get root 4.84, which is equal to 2.2. Coach B's standard deviation is higher. And that tells us that the range of running speeds of his runners is going to be greater, and so he's likely to have more runners who are faster. So in an event where only the faster runners are running, Coach B is going to have a greater number of faster runners because of that higher standard deviation. So some explanation along those sorts of lines will do the trick. All right, question number 3. So this is the binomial distribution. We're dealing with a variable, I've called it x. It's binomially distributed with 36 trials and a 0.015 probability of success. Question number 1 wants us to find the probability that x equals 2. I'm showing you here a Casio, it's a Casio FX CG50. It's one of the GDCs. I'm going to type in 2 for the number of successes, 36 for the trials, p is 0.015, and we can see the probability of that is 0.08479. For part 2, we want the probability x is greater than 3. Now, because this is discrete data, we're going to look at numbers that are 4 or above. So back to the binomial section of the calculator, set my lower as 4 and go up to 36, and then execute that, and we can see we get 2.03 times 10 to the minus 3. I'm not going to write them out in standard form. I'm going to write it as an ordinary number. For B, we're increasing the number of trials here. So we've got 260 trials with the probability of success of 0.015. The 5% significance level, I'm going to split between both ends. This is a two-tailed test. I know this because it's asking if the proportion has changed. It hasn't said has it increased or decreased, it's just changed. So we're going to have 2.5% at each end. Then the probability of y being greater than or equal to 8. Set my lower as 8, set my upper as 260. Of course, there's 260 trials now, so I'll change that. The probability of success is still the same. And so it's a 0.0441. Now that's important because it is greater than the threshold we were looking at, 0.025. Therefore, we will accept the null hypothesis. There is not sufficient evidence to suggest that the problem has changed. Okay, the large data set question A, that's systematic sampling. For B, it may be that rainfall may contain the total rainfall entries, so she may need to clean those first, just to check. Then for C, the units of the gradient is going to be millimeters per hour. And to interpret the y-intercept of the regression line, we're going to get the total rainfall with 0 sunshine. For D, well, looking at that gradient, that's a positive gradient, so we would expect the opposite thing to happen there. So the more sunshine, the more rain, although that does sound counterintuitive. For E, the hypothesis test, so we're looking at a value of rho. Is it 0 or is it less than 0? The alternative hypothesis. It tells us the p-value comes out as 0.015. That's important because it's less than 0.05. We shall therefore reject the null hypothesis, accept the alternative hypothesis, and that there is sufficient evidence to support the teacher's claim. Okay, for F, the sample is just the rainfall and sunshine from May to October in 2015. And then the population, or a possible population, could be the rainfall and the sunshine over the course of the whole year. There are alternatives for the population you could use. Okay, normal distribution. The men are normally distributed with a mean of 183 and a standard deviation of 4.9. So I'm going to use M as my variable. That's normally distributed. 183 is my value of mu, and 4.9 squared. Standard deviation of 4.9. Probability of picking a man at random greater than 186 centimeters. Well, I'm going to go to stats section again. We are looking at distribution here, normally distributed, normal cumulative distribution. Let's set our lower as 186. I set my upper as something large because it forces me to. Sigma's 4.9. The mean is 183. And when I execute that, it tells me the probability is 0.27018787, etc., etc. I'll round that to 0.270. For part 2, we're looking for picking one at random in between 175 and 185. So a small amendment to the calculator, just set the upper and lower. So the lower is 175, the upper is 185, and we can get a probability of 0.607. My p-value. For B, so B is dealing with the distribution of the heights of the women in the club. So I'm going to introduce a new variable W, which is also normally distributed. It doesn't tell us mu or sigma. That's what the question is asking us to find out. It does tell us the probability of picking a woman at random below 170 centimeters is 0.4. And the probability of picking a woman at random who is taller than 175 centimeters is 0.15. So I can use the formula that converts a normal distribution onto the standardized normal. So that's going to be x minus mu over sigma. To work out the z value that corresponds with that, I'll jump back to my GDC. If I go to distribution, normal, the inverse normal section, I'm going to set the area to 0.4. The tail's gone to the left, standard deviation 1 and mean is 0, and we can see the z value there, negative 0.2533. Then for the one larger than 0.15, I'll jump back to my GDC. This time I'm going to set the tail going to the right. I set the area as 0.15. And if I execute that, it gives me a z value 1.0364, etc., etc. Essentially, we're now dealing with two simultaneous equations, so you can go about solving these in whichever way you prefer. You can just solve them on a GDC if you like. I multiplied both sides by sigma for both of the equations, and I've subtracted one equation from the other, divided through, and we get sigma, and then we get mu. So 3.88 and 171. For the probability of picking a female between 170 and 175, well, we actually have those probabilities given to us in the question for the areas outside of that, 0.4 and 0.15. So I can add those together and subtract them from 1 to get a probability of 0.45. Then for the men between 170 and 175, I need to go back to my GDC, plug in the lower as 170, the upper as 175, with the same mean and standard deviation that we had before, and that probability comes out as 0.04728, etc., etc. And we're going to multiply those two probabilities together. 0.021. Right, question 6 is the discrete random variable. So we've got a little formula to work out the probability of each one of them. Now we know if we add them all together, they have to sum to 1. So essentially plugging 2, 4, 6, etc. in for my values of r up to 2n and summing them, that's going to be equal to 1. So the actual probabilities themselves form an arithmetic series. So I can use the summation of an arithmetic series formula, n over 2, lots of 2a plus n minus 1d. So n over 2, lots of 2 times 2 plus n minus 1 times 2. And that's going to be equal to k. If you imagine, I've just multiplied everything by k to bring it onto the right-hand side there. Simplify what's inside the brackets. And we get n over 2 lots of 2n plus 2 equals k, and cancel the 2's. So n times n plus 1 is equal to k, which is what the question wanted. For part B, this time it gives us n to be 20, so a quick calculation to work out k. 20 times 21 is 240. we're looking for values in between 16 and 26 for R. So those are going to be 16, 18, 20, 22, and 24. If we sum those together over 240, that simplifies to 100 over 420, simplifies down to 5 over 21. For part C, we're looking at the equation x squared plus gx plus 3g minus 5 equals 0. You'll notice a mistake there. I've written 3x minus 5. It should be 3g minus 5. Please don't write in. I've spotted it, and therefore it doesn't count. My A is 1, my B is g, and my C, I've corrected it there, is 3g minus 5. We're going to do the discriminant test because we want this to have no real roots. So b squared minus 4ac will be less than 0 if it's got no real roots. So in this case, g squared subtract 4 times 1 times 3g minus 5, which is less than 0. Expand that all out. G squared minus 12g plus 20 is less than 0. And factorize it. G minus 10 and g minus 2 is less than 0. So it's the values of g in between 2 and 10 which we're looking for. So I'm going to extract g to be 4, 6, and 8 out of that. And so we're looking at 4, 6, and 8 out of the 420. And that simplifies down to 18 over 420, or 3/70ths for a full simplification. Well done if you managed to work that one out. It's quite a tricky one to end with. Right. Bye.